transcription and translation chapters and good. All right, so we just talked about this. I'm kind of just backing up a little bit to remind you where we were. We had started the initiation of transcription at this point, so we've already translated the mRNA transcript, and if we're in a eukaryotic cell, we don't just make a copy. We have that pre-mRNA that then has to get capped with a 5' cap. It has to get a poly A tail put on the end. It has to get spliced out. The exons get spliced out. I'm sorry, the introns get spliced out, and then the exons are put back together by that cool complex of protein and RNA that's called a spliceosome. Then that's your actual mRNA transcript that can exit the nucleus, go out into the cytoplasm, and be turned into a protein at that point, or provide the instructions for a protein. And so we describe this process where you have your ribosome. Ribosomes can be free in the cytoplasm, or they can be bound to the endoplasmic reticulum, and they can go back and forth between free and bound. So it's not as though they're always in the cytoplasm or they're always stuck to the endoplasmic reticulum. They can go back and forth. There's no difference between a ribosome that's free floating in the cytoplasm and a ribosome that's stuck to the endoplasmic reticulum. And so it's basically walking you through the steps of how do we initiate translation. And again, just to remind you, translation is where we're taking the language of a nucleic acid and we're turning it into the language of a protein. And so it's basically saying at first you have to have your small subunit, also known as a 30S subunit, and it has a little binding site for that little 5' cap for your mRNA transcript. So you have your small subunit, you have your little bound mRNA transcript. Make this pretty, I'll put that in a different color. And we have our initiator tRNA molecule. Do you guys remember which tRNA molecule is our initiator?
Methicillin.
Methionine.
Methionine.
Close. Close enough. Yeah. Close enough. So here's our little upside down tRNA molecule. This guy's going to be holding methionine. He's going to have the anticodon for methionine. So that's how we start the translation process. Once this ribosome is going to kind of travel down the mRNA until it gets to that start codon. Once it gets to the start codon, there'll be proteins that are called initiation factors, and they will basically allow the full complex to form. So the large subunit of the RNA or of the ribosome will now come into place via these little initiation factors, and now we have the full translation initiation complex. We're ready to go. And we already talked through this process before. We have the Environmental Protection Agency making our proteins, our E, P, and A. So basically, here we are with our start codon. Here's the tRNA molecule with the anticodon, and it's attached to methionine. Remember, we have those little enzymes that put these amino acids on the tRNA molecule. They're called aminoacyl tRNA synthetases. And there's 20 different aminoacyl tRNA synthetases, one for each amino acid. And so this is the specific one for methionine. So this is considered a charged tRNA particle. Once it gets here, then your next codon will tell the cell what's the next tRNA molecule that needs to bind here. It will bind here. We will form a peptide bond between methionine and the next amino acid. After we form that peptide bond, these two tRNA molecules that occupy the P and the A site will shift forward. So this one will go to the E site, which is the exit site, and the one that was in the A aminoacyl site will go to the peptidyl binding site. So we just shift everything forward, and at the same time, we're going to shift the mRNA transcript up by 3 units. Okay, so we're just basically pulling everything through 3 nucleotides at a time, and for every 3 nucleotides, we get a new tRNA molecule that comes in there. And that's how you make your proteins. Pretty amazing. Okay, so that's how we initiated the process. Now we have to elongate the transcript. You have to elongate the polypeptide chain. And again, this is kind of divided into 3 steps. The first, and we kind of walked through them in the previous slide, you have to recognize the next codon. So the next 3 mRNA nucleotides is the next codon. So we have to know, okay, what codon comes next? Then, once we recognize that codon, the tRNA molecule can come into that A site. Then we have to form a peptide bond between the amino acid from the A site and the amino acid from the P site. We've got to form that bond together to make the next amino acid in the chain. And And then we have to do what's called translocation, which just means those tRNA molecules shift up. And I'll show you again in the picture. We'll walk through that one more time. Costs us a little bit of energy to do this. No big surprise there that this is not a free energy. Anytime you're building something, endergonic, non-spontaneous, anabolic, all of those terms coming back from that test a few tests ago should come back into play now. We're building something, so it requires some energy. Same direction here though. Remember when we copied our genome, everything had to be copied in the 5' to 3' direction? Same thing is true when we are translating a protein. That mRNA is read in the 5' to 3' direction. Okay, always, always, always. So let's just walk through that one more time, those 3 steps of elongation. So we initiated the process by having the small subunit with the special initiator tRNA molecule that's bound to methionine, and the small subunit of the ribosome all form this complex. The small ribosomal subunit scans the 5' mRNA message until it gets to that start codon. Then those initiation factors help the large subunit assemble, so we have our translation initiation complex at that point completely formed. Now we're going to elongate the polypeptide chain. So here's our polypeptide chain coming out of the exit tunnel of the large subunit here. So what's going to happen? The first thing is you have to recognize the next codon. Which amino acid comes next? It's going to be specific. Remember, each codon will code for one specific amino acid. Okay? So here we go. I don't know what this is. Let's pretend it's valine. Why not? Here's valine. The codon for valine is here. Here's the tRNA molecule with the anticodon for valine. Valine is already loaded onto the tRNA molecule, so it's a charged tRNA molecule ready to add its amino acid to the protein. It's going to come into the A site. Costs us a little energy for this next part to happen. Then we're going to have to basically, we have this growing polypeptide chain, but we need to add the next amino acid. When we put 2 amino acids together, that's called a peptide bond. So we have to make a peptide bond. All of these terms come back from, basically the first few lectures that we had in class. So we're going to build a peptide bond here. And then that growing polypeptide chain gets transferred to the tRNA molecule that was in the A site. Now we need to translocate everything up one position. So that's our 3rd step, and it also requires some energy. So here we go. This tRNA that was in the P site moves up to the E site, exits. The tRNA molecule that was in the A site moves up to the P site. Now he's holding the polypeptide chain, and he's waiting for the next tRNA molecule to come in so that the next amino acid can be added. So that's elongation. That's how we build a protein. Now, is the protein ready to go? Is it ready to go do its job yet?
Is the red part the protein or the purple part?
The red part is the mRNA transcript. This is the instructions. The purple is the protein.
Oh, okay.
Okay, this is the polypeptide chain. It goes out the exit tunnel, and the translocation involves both the tRNA molecules moving as well as the message. The message has to move up as well. Okay? So it's like you're scanning 2 things at the same time. And this happens really rapidly, which is amazing. How do we stop? Stop codon. Remember, we have those 3 codons that do not code for an amino acid. You don't have to know them, but T2AG, UGA, I think UAA is the last one. So any of those 3 codons basically says, stop, you're done, quit. You've made your protein. So basically, once you get to that stop codon, now there's a instead of having a tRNA molecule with a amino acid attached, you get something that's called a release factor that's now going to come into that A site. And when the release factor comes into that A site, it basically adds a water molecule. Think about like a hydrolysis reaction when we add a water molecule in. And that allows the polypeptide chain to pop off of the ribosome. So now our polypeptide